Programming Sega Genesis games, like most video games, involves writing code that controls the game's behavior, including character movement. Here's a basic overview of how developers programmed character movement on the Sega Genesis. One. Understanding the Sega Genesis. Hardware, CPU. The Sega Genesis is powered by a Motorola 68000 CPU, which is a 16-bit processor running at about 7.6 MHz. It also has a secondary processor, the Zilog C80, for sound. Graphics. The console uses a video display processor, VDP, to handle graphics, with a resolution of 320 by 224 pixels, and a limited palette of 64 colors on screen at a time. 2. Programming language, assembly language. Most Sega Genesis games were programmed in assembly language specifically for the Motorola 68000 CPU. Assembly language is a low-level programming language that is closely related to the machine code that the CPU executes. C language. Some later games or more complex systems might have used C for parts of the code, but the tight control and efficiency required for early console games made assembly the primary choice. Five. Scrolling and background interaction. Scrolling. Many Sega Genesis games feature scrolling backgrounds. When the character moves, the game might scroll the background to give the illusion of a larger world. This involves updating the background position as the character moves. Interaction with environment. The character's movement can also trigger interactions with the environment, such as picking up items, entering new areas, or triggering scripted events. 6. Optimization. Performance. Since the Sega Genesis has limited processing power and memory, developers had to carefully optimize the code to ensure the game ran smoothly. This included efficient memory usage, minimizing the number of calculations per frame, and optimizing the rendering of sprites. Seven. Tools and development kits. Development kits. Sega provided official development kits to game developers, which included tools for coding, debugging, and testing games. These kits often included assemblers, debuggers, and emulators that allowed developers to write and test their code on PCs before running it on the actual Sega Genesis hardware. In summary, making characters move in Sega Genesis games involves programming logic that responds to player input, updates the character's position, handles animations, and interacts with the environment. This process required careful coding, usually in assembly language, to make efficient use of the console's limited hardware capabilities. Three. Character movement logic, sprites. Characters in Sega Genesis games are typically represented as sprites, 2D images that can be moved and animated independently of the background. Input handling. The game continuously checks for input from the controller. When a player presses a directional button, e.g., left, right, up, down, the game registers this input. Updating position. Based on the input, the game updates the character's position on the screen. For example, pressing the right button might increase the character's x-coordinate, making them move to the right. Animation. Along with updating the position, the game also changes the sprite's image to match the character's action, e.g., walking, jumping. These animations are often done by cycling through different frames of the sprite. 4. Movement and collision detection, velocity and acceleration. To create smooth movement, the game might calculate the character's velocity, speed, and acceleration change in speed. This allows for more complex motion, such as gradual speeding up or slowing down. Collision detection. The game checks if the character's new position would cause a collision with other objects, like walls, platforms, or enemies. If a collision is detected, the game might stop the character's movement or trigger an event, like taking damage. To program a sprite or character for a Sega Genesis game, developers use a combination of pixel art, assembly language, or sometimes C, and the console's graphics hardware. Below is an overview of how this process works, including how to create and manipulate sprites. 1. Creating the sprite, character, art, pixel art. sprites on the Sega Genesis are made using pixel art, where each pixel is individually colored to create a character or object. Due to the limited resolution and color palette, artists must work within constraints, e.g., 320 by 224 resolution and a palette of 64 colors on screen. Tiles. The Sega Genesis uses tiles to create sprites. A tile is a small, 8 by 8 or 16 by 16 pixel block of graphics. Multiple tiles are combined to form a complete sprite. 3. Programming the sprite in assembly language, loading sprite data in the game's code. The sprite data, i.e., the pixel information, is loaded into the Sega Genesis's video RAM VRAM. This is typically done using assembly language to control the graphics hardware directly. Setting up the sprite, you define the sprite's position on the screen, size, and which tiles to display. The Sega Genesis has a sprite attribute table SAT that holds this information, position, coordinates on the screen where the sprite will appear, x, y, tile index, which tiles to use from VRAM to form the sprite, attributes. This includes flipping the sprite horizontally or vertically, priority over background layers, and palette selection. 2. Preparing the sprite for the Genesis, graphics tools. Developers use specific tools to create and edit sprites. In the past, these might have been custom tools or specialized software like Deluxe Paint. Today, you can use modern pixel art tools like a Sprite or Photoshop, but the artwork must be exported in a format compatible with the Sega Genesis, converting to sprite data. The pixel art is then converted into a format that the Sega Genesis can understand, typically an array of data representing each tile. This data includes color information, and sometimes a palette index that references the colors to be used. 4. Making the sprite move, input handling. The game continuously checks for input from the controller, e.g., pressing the right arrow key. When input is detected, the code adjusts the sprite's position by changing its x or y coordinates, updating the screen. The game's main loop updates the sprite's position on the screen based on the player's input or logic. The CPU updates the SAT to reflect the new position of the sprite, animation. To animate the sprite, e.g., making the character walk, the game cycles through different tiles that represent different frames of the animation. For example, if the character is walking, the game might alternate between different sprite tiles that show different light positions. 5. Handling collisions, collision detection. The game needs to determine when the sprite collides with other objects, like walls or enemies. This is done by comparing the sprite's position to the positions of other objects. If a collision is detected, the game might prevent further movement in that direction or trigger a response, e.g., taking damage. 6. Optimizing the sprite. Performance, memory management. Since the Sega Genesis has limited memory, developers must manage how many sprites are on the screen at once and how they are stored. Sprites that are off-screen or not needed might be unloaded from VRAM to free up space. Sprite limits. The Sega Genesis can handle a maximum of 80 sprites per frame, with a limit of 20 sprites per scanline horizontal line on the screen. If these limits are exceeded, sprites may start to flicker or disappear. Sprite limitations. 7. Tools and emulators, development tools. Developers use tools provided by Sega and third-party developers to program, test, and debug their games. Today, you can use emulators and modern tools like the Sega Genesis Development Kit, SGDK, to develop games. Testing on hardware. After programming, the game would be tested on actual Sega Genesis hardware to ensure it worked correctly, considering all hardware constraints. Example of simple assembly code for moving a sprite. Here's a very simplified idea of what some assembly code might look like to move a sprite in response to input. Load the sprite's x coordinate. Move w, x coord do. Check if the player is pressing the right button. BTST #right button, controller input BQ. No right press. If pressed, increase x coordinate. ADDW number 2 do. No right press. Update the sprite's position. Move, W do, X coord, update sprite attribute table with new X coordinate. Move W do, sprite table ADDR. Conclusion: programming a sprite for the Sega Genesis involves a combination of pixel art creation, data management, and assembly language coding to control the character's movement and interaction with the game environment. Despite the hardware limitations, developers were able to create visually impressive and responsive characters that are still fondly remembered today. Programming games on a calculator, especially graphing calculators, like the ti-84, is a fun and educational way to learn programming concepts. Most graphing calculators allow you to write and run simple programs using a built-in programming language, or by using assembly language. Here's how you can get started. 1. Choosing the calculator model and language. TI-83/84 series. These are some of the most popular graphing calculators used in schools. They support TI Basic, the built-in programming language, and assembly language. Other models. Different calculators have different capabilities. For example, the Casio FX CG50 supports Casio Basic, while HP calculators might support RPN, reverse Polish notation programming. 2. Learning TI Basic for TI calculators, accessing the program editor. On a TI-83/84, press PRGM, then scroll to New, and press Enter to create a new program. Name your program, and then you'll be taken to the program editor. Writing simple code. TI Basic syntax is straightforward. Here's a simple example of a number guessing game. C1 Rome, disp guess a number, disp between 1 and 10, 1a, 10b, rand int, a, b, c, input your guess, x, if x equals c, then, disp correct, else, disp wrong, disp the number was c, end. Running the program. Exit the editor by pressing second plus quit. To run the program, press PRGM, select your program from the list, and press enter, then enter again to execute it. 3. Creating simple games. Text-based games. You can create text-based games like Guess the Number, quiz games, or simple choose-your-own-adventure stories. Basic graphics. You can use simple graphics commands to create games like Snake or Pong. Here's a quick example of drawing a line. Line 0, 0, 94, 62. This draws a line from the bottom left of the screen to the top right. Control structures. Use loops for, while, conditionals, if then else, and variables to create more complex games. For example, a simple loop for moving a character on the screen might look like this. Running the program. Exit the editor by pressing second plus quit. To run the program, press PRGM, select your program from the list, and press enter, then enter again to execute it. 3. Creating simple games. Text-based games. You can create text-based games like Guess the Number, quiz games, or simple choose-your-own-adventure stories. Basic graphics. You can use simple graphics commands to create games like Snake or Pong. Here's a quick example of drawing a line. Control structures. Use loops for, while, conditionals, if then else, and variables to create more complex games. For example, a simple loop for moving a character on the screen might look like this. Sir home, 0x0y, repeat Jekki equals 105, output, y, x, 0, get keek, if k equals 24y plus 1y, if k equals 25y 1y, if k equals 26, x1x, if k equals 34x plus 1x, C1 Rome, end. This program allows you to move a character O on the screen using the arrow keys. 4. Using assembly language. Why assembly? Assembly language allows you to create much faster and more complex games, but it is harder to learn and use. Learning assembly. If you're interested in writing assembly programs for a TI calculator, you'll need to learn Z80 assembly for the TI-83/84 series. You'll also need a way to transfer your programs to the calculator, using a USB cable or through an emulator. Tools. Use an assembler like TASM or Spasm to write and compile your assembly code, and then transfer the compiled program to your calculator. 5. Transfer and share programs. Calculator to calculator. You can share programs directly between TI calculators using a link cable, using a computer. You can write programs on your computer and transfer them to your calculator using TL Connect software and a USB cable. This is especially useful for more complex projects or if you're using assembly language. Conclusion: programming games on a calculator, especially in TI Basic, is a great introduction to programming. You can start with simple text-based games and move on to more complex projects involving graphics and even assembly language if you want to push the calculator's capabilities. It's a fun way to learn programming logic and problem solving, all while working within the constraints of the calculator's limited resources. 6. Using online resources, online forums and communities. There are many online communities like Semadec or TI Planet, where you can find tutorials, code snippets, and support for programming on calculators, pre-made libraries. You can also find libraries and pre-made games online that you can study or modify. 7. Emulators, testing on emulators before transferring your game to the calculator. You can test it using an emulator, like ti-84 or WabbitEmu. This allows you to debug and refine your game without having to repeatedly load it onto your calculator. Transfer and share programs, 5. Transfer and share programs, calculator to calculator. You can share programs directly between TI calculators using a link cable, using a computer. You can write programs on your computer and transfer them to your calculator using TI Connect software and a USB cable. This is especially useful for more complex projects or if you're using assembly language. 6. Using online resources, online forums and communities. There are many online communities like Semadec or TI Planet, where you can find tutorials, code snippets, and support for programming on calculators, pre-made libraries. You can also find libraries and pre-made games online that you can study or modify. 7. Emulators, testing on emulators before transferring your game to the calculator. You can test it using an emulator, like ti-emu or WabbitEmu. This allows you to debug and refine your game without having to repeatedly load it onto your calculator. Conclusion: programming games on a calculator, especially in TI Basic, is a great introduction to programming. You can start with simple text-based games and move on to more complex projects involving graphics and even assembly language if you want to push the calculator's capabilities. It's a fun way to learn programming logic and problem solving, all while working within the constraints of the calculator's limited resources. Tiger Electronics created the Terminator 2 Judgment Day handheld game in the early 1990s, which was one of their many LCD, liquid crystal display, games. Here's an overview of how they developed the game and the technology behind it. 1. Concept and design, licensing. Tiger Electronics obtained the rights to create a game based on the popular movie Terminator 2 Judgment Day. The game was designed to capture the essence of the film, focusing on its characters and themes, game design. The game designers conceptualized gameplay mechanics, level designs, and how players would interact with the game. The aim was to create an engaging experience that reflected the action and narrative of the film. 2. Hardware development, LCD technology. Tiger Electronics used LCD screens for their handheld games, which were simple, low-power displays. Each game featured a fixed background, with animated characters and objects overlaid on the screen, buttons and controls. The game included buttons that allowed players to interact with the game, e.g., moving characters, shooting, etc. The design needed to ensure that the controls were intuitive and responsive to player input. 3. Game mechanics, gameplay style. The game typically involved simple mechanics, where players would navigate through levels, avoid obstacles, and defeat enemies. The gameplay was often non-linear, with players needing to make quick decisions, graphics and animation. The graphics were created using a series of static images and simple animations. Designers created sprites for the characters and enemies, and the game used a limited color palette, typical for LCD technology at the time. 4. Programming, microcontroller. The game was programmed on a microcontroller, which handled the logic and timing of the game. Programming was done in assembly language, or low-level languages that could efficiently manage the limited resources of the hardware. Game logic. The programming included collision detection to determine when the player hits an enemy, scoring systems, and condition checks for winning or losing scenarios. 5. Testing and iteration. Playtesting. After development, the game underwent rigorous playtesting to identify any bugs or areas for improvement. Testers would play the game to ensure it was fun, challenging, and worked correctly. Feedback and adjustments. Based on feedback, developers would adjust gameplay mechanics, difficulty levels, and control schemes to enhance the overall player experience. 6. Manufacturing, production. Once the game was finalized, it went into production. This involved creating the physical units, including the LCD screens, circuitry, and housing. Quality control. During manufacturing, quality control ensured that each unit worked as intended and met safety standards. 7. Marketing and distribution, promotional strategy. Tiger Electronics marketed the game alongside the movie's release, leveraging its popularity to attract buyers. The marketing included advertisements, packaging design, and placement in retail stores. Sales and distribution. The game was distributed through various retailers, and its success was influenced by the popularity of the Terminator franchise. Conclusion. Creating the Terminator 2, Judgment Day handheld game by Tiger Electronics involved a multifaceted approach, from conceptualizing the game and designing hardware to programming and manufacturing. The combination of simple yet engaging gameplay, recognizable characters, and effective marketing contributed to its appeal among fans of the film and handheld gaming enthusiasts during that era. While the technology was relatively simple compared to modern gaming, it captured the spirit of the film and provided entertainment to many players. Programming a game similar to Terminator 2, Judgment Day on a calculator can be a fun project, especially if you're using a graphing calculator, like the ti-84. While you won't be able to replicate the full complexity of the original game, you can create a simplified version using TI Basic or a similar programming language for your calculator. Here's a step-by-step guide to get you started. 1. Conceptualize your game, game mechanics. Decide on the core mechanics of your game. For example, you might have the player navigate a character through levels, avoid enemies, and shoot at targets. Objective. Define the objective of your game, such as reaching a certain point or defeating enemies. Graphics. Plan out what your characters and enemies will look like. Remember that on a calculator, graphics will be limited to simple pixel representations. 2. Setting up your environment, access the program editor. On a ti-83/84 calculator, press the PRGM button, then select New to create a new program. Give it a name, familiarize yourself with commands. Learn the basic TI basic commands, such as ser home, disp, input, and control structures if4, while. Basic game. 3. Basic game structure. Here's a simple example of how you might structure a text-based Terminator-inspired game. This example will focus on a simple shooting game, where the player tries to hit targets. Example game code in TI Basic, C1 Rome, disp Terminator game, disp A, shoot B, quit, 0 score, 0 enemies, repeat get key equals 105. Loop until the user presses entry. Randint 1, 10 enemies. Randomly generate enemies. For I1 enemies. Output I1 target show targets. End. Get key. Get player input. If k equals 1, if button A is pressed. If enemies 0. Score plus 1 score I increment. Score for hitting a target. Disp hit. Else. Disp miss. End. If k equals 2, if button B is pressed. Disp quitting. Stop. End. Ser home. Disp score. Score. End. 4. Explaining the code. Initialization. The game clears the screen and displays the title. Game loop. The loop continues until the player presses the enter button. Random target generation. It generates a random number of targets enemies each round. Player input. The player can press button A to shoot or button B to quit. Scoring. The score increases if the player shoots at targets. Display score. The current score is displayed on the screen. 5. Enhancements and features. Once you have the basic game working, consider adding enhancements. Multiple levels. Increase the difficulty by adding more enemies, or faster moving targets as the score increases. Graphics. Use pixel graphics with the line, circle, or point commands to create a more visual representation of the game. Sound effects. Some calculators support basic sound commands. You can add sound for shooting or scoring. Live system. Implement a system where the player has a limited number of lives or health points. 6. Testing and debugging. Playtest. Run your program multiple times to ensure everything works correctly. Debugging. Check for errors in logic or syntax. TI Basic provides error messages that can help you identify issues. Creating a game like Snake's Revenge, a sequel to the classic Snake game, on a calculator involves programming logic for movement, collision detection, and game mechanics. Here's a comprehensive guide on how to design and program a simplified version of Snake's Revenge using TI Basic on a ti-84 calculator, or a similar graphing calculator. 1. Game concept. Objective. The player controls a snake that grows longer as it consumes food while avoiding collisions with walls and itself. Gameplay mechanics. The snake moves continuously in a direction. The player can change the snake's direction using the calculator's arrow keys. The game ends if the snake collides with the walls or itself. Food appears randomly on the screen for the snake to eat, which increases its length. 7. Transferring and sharing. Transfer programs. If you create your game on a computer, you can use TI Connect to transfer it to your calculator. Sharing. Share your code with friends or online communities that focus on calculator programming. Conclusion. Creating a simple game inspired by Terminator 2, Judgment Day on a calculator is an engaging way to learn programming concepts and have fun with your calculator. While the graphics and gameplay will be limited compared to a full-fledged game, you can still capture the essence of the movie and create an entertaining experience. Start simple, and as you become more comfortable with the programming language, you can add complexity and features to your game. 2. Setting up the environment. Access the program editor, press PRGM, then select New, and name your program. Familiarize with TI Basic commands. Understand commands like CL home, output line, and control structures like if for and while. 3. Basic game structure. Here's a simplified version of how you might code a snake game. Due to the limitations of TI Basic, this example will cover the core mechanics without full graphics. If d equals 0, x plus 1x. If d equals 1y 1y. If d equals 2x 1x. If d equals 3y plus 1y. Semicolon. Move right. Move up. Move left. Move down. If x 0 or x 10 or y 0 or y 10. Collision with walls. Disk game over. Stop. End. Pause 0.5. Speed. End. Semicolon. Control game. 4. Explaining the code. Initialization. The game clears the screen and initializes variables for the snake's length, position, and direction. Main game loop. This loop continues until the game ends. Home. 0L. 5x 5y. 0d. I length of snake. Starting position, direction, 0 equals right, 1 equals up, 2 equals left, 3 equals down, colon. Repeat 0. Semicolon. Main game loop. C1 Roam. For 1L. Semicolon. Draw the snake. Output y, I. Display. Snake body. End. Output y, x, 0. Semicolon. Display. Snake head. Randint 1, 10f. Position. If f equals x, and y equals f. Position equals snake head. L plus 1L. Semicolon. Random food. Semicolon. If food, I increase. Length. Randint 1, 10, x. I generate. New. Food position. End. Get keek. Semicolon. Get player. Input. If k equals 24 n. D number 3. D3. if k equals 25, and d number 0, d0, if k equals 26, and d1, d1, if k equals 34, and d number 2, d2, semicolon, up, semicolon, down, I left, semicolon, right. 4. Explaining the code, comma, initialization. The game clears the screen and initializes variables for the snake's length, position, and direction, comma, main game loop. This loop continues until the game ends, comma, drawing the snake. The snake's body is drawn on the screen by looping through its length and placing asterisks for the body and in 0 for the head, comma, food generation. The program randomly generates a food position. If the snake's head reaches the food position, the length increases, and new food coordinates are generated, comma, direction control. The player can change the snake's direction using the arrow keys, while ensuring it cannot turn directly back on itself, comma, movement. The snake moves in the current direction by updating its x and y coordinates, comma, collision detection. If the snake collides with the walls, the game ends with a message, comma, game speed control. The pause command controls how fast the game updates. Transfer program. 7. Transferring and sharing, comma, transfer programs. Use TI Connect to transfer your game to your calculator, comma, sharing. Share your code with friends or communities focused on calculator programming. Conclusion. Creating a game like Snake's Revenge on a calculator using TI Basic is a rewarding project that helps you learn programming concepts. While the graphics and mechanics will be simplified compared to modern games, you can still create an engaging and fun experience. Start with a basic version, and as you gain confidence, add more complexity and features to enhance your game. 5. Enhancements and features. Once the basic game is functional, consider adding these features, comma, self-collision. Implement logic to check if the snake's head collides with its body, comma, scoring system. Keep track of the score based on how many food items the snake consumes, comma, multiple levels. Increase difficulty by speeding up the game or adding obstacles, comma, graphics. Use more elaborate graphics commands to draw the snake and food more visually. 6. Testing and debugging, comma, playtesting. Run the game multiple times to test its functionality, comma, debugging. Check for errors in logic and make adjustments based on gameplay experience.